Welcome back. In the last video we talked about our first operation in R2. Recall, this operation was called the to-norm. The to-norm of a vector was a map that input vectors in R2 and output real numbers. So this is kind of formal notation to say the to-norm is a maps vectors in R2, this is the domain, into the real numbers. The output of the to-norm is a real numbers into the real numbers. And I wanted to recall that if we said that we had a vector, perhaps we call it x1, y1, then the to-norm had very special notation. It's these double absolute value bars that you may have never seen before. And it's written as the square root of the sum of the squares of the components of this vector. So these are double vertical bars. Inside the to-norm is a vector. This is a subscript, so it's written on the kind of on the bottom on the right hand vertical bar. So you see this, here's the left hand vertical bar, here's the right hand vertical bar, and then as a subscript down below we write 2 to represent that this is the to-norm. And remember that the way we calculate this to-norm, this is a real number. The output is the sum of the squares of the inputs. And recall that this comes from the Pythagorean theorem. All right, so this is the first operation that we have where the input of the operation is a single vector. That's what we expect in. And the output is a real number because when we take the sum of the squares and then square root it, we get a real number out. In this video, we're now going to talk about a next operation in R2, which is called vector addition. Okay, so this is going to be a new operation. We now define a new operation, vector addition. And this is going to be pretty crazy. We have an addition symbol, very, very similar to the addition symbols that we've seen before, except on the left-hand side and the right-hand side of this addition symbol, we're going to put vectors, and we're also going to output a vector. So this says, let addition be a map from a two-dimensional vector and another two-dimensional vector, and then we're going to produce a two-dimensional vector. So vector addition is a map that takes in two vectors and outputs a vector. See it? Vector addition takes on the left of vector addition, we're going to put a vector. On the right, we're going to put a vector, and we're going to produce a vector. All right. So here we go. So let's start with two vectors. Let's let x be the first vector. And we'll let y be the second vector. And then we'll go ahead and look at the sum of these vectors. So this is what we call vector addition. Be careful, this symbol looks exactly like scalar addition that you've seen in your past life, but it's not. And the reason it's not is that the left hand is not a scalar and the right hand is not a scalar. All right, so here we go. Here we had x1, y1, and on the right we have x2, y2. In vector addition, we are literally just going to add the components. Here we have x1 plus x2, y1 plus y2. All right. So literally, vector addition takes the sum of two vectors, and then to get the output, you just add the components of the vectors. And there's a way that you can visualize this. We can visualize this as something called the triangle law. All right? So in the triangle law, la, 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 la. First thing we're going to do is we're going to go along x 1 units that way and y 1 units that way. That's called x, right? So here's x. Here's my vector x, which is the first thing that I'm trying to add here. So here's my vector x. All right. Next thing we're going to do is go x2 units along this way and y2 units along this way. This will be my vector y. Okay. So notice this distance right here was x2. And then this distance right here was y2. So if you looked at this point along the axis, you would have x1 plus x2. So this would be x1 plus x2. And then the distance along here would be y1 plus y2. And then the sum is the vector that results from that. It's the vector connecting the origin, the initial point, to this one. Here's the sum. This is x plus y. Because first I go along x, then I go along y. Notice that these three together form a triangle that we're visualizing as the triangle law. Okay. Let's take a look at an example of how this might work. To do so, we're going to add 4, 1 with 1, 3. All right? So the solution to this, quite simple. Perhaps we call this first one x and the second one y. X plus y is equal to 4, 1 plus 1, 3, which is 4 plus 1, 1 plus 3, which is 5, 4. All right, if we look at, let's visualize this just to kind of make this come home. One, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. All right, 4, 1. So I go 4 over 1 up. Here's my x vector. This is my x vector. All right. My y vector, I go 1 over and 3 up. 1, 2, 3. Notice that the initial point of this y vector is the terminal point of the x vector by this. I start y at the end of x. So now we have here, this is y. And notice we have that beautiful box. The sum of these, the vector 5, 4, starts at the origin, because I haven't said where else that it starts, and it goes all the way to, now this is the vector x plus y. There's the triangle. X plus y, I go along x, along y, and now I get the vector that connects the initial point of x to the terminal point of y, where y's initial point is the terminal point of x. Okay. Some interesting notes should be made here. First and foremost, we can prove quite quickly, in fact, that it doesn't matter what order we do this operation in. When I do this first vector addition, I literally just add the components inside, but then this addition here is now addition between real numbers. This addition these are different additions. We got to be really careful about that. This addition is vector addition. This addition is scalar addition. They're different additions. They act in different spaces. This scalar addition can be done in any order, which means I can switch the order of this because of the behavior of scalar additions in real numbers. But then I can use the definition of vector addition to break these apart. And what we've just shown is we now have an algebraic identity that says that vector addition can be done in any way. This is called commutativity of vector addition. Meaning that you can do it one way or the other. We can visualize this using what we call the parallelogram law. Okay, I can go along x first, then go along y, to get the sum x plus y, or I can go along y first, then go along x, and I still get the sum y plus x. So this whole thing is x plus y, x plus y. I get the same vector as when I write y plus x, y plus x, which is mathematically, this is the algebraic representation, this is the graphical representation of that reality. Okay, in the next video we're going to talk about scalar vector multiplication. See you there.